All right. So, in the last lecture, we saw the Poisson approximation, right? We saw the Poisson distribution and how you can approximate the distributions of balls into bins using the Poisson approximation, right? So, we said that um, the balls and bins process was where you have balls being thrown into bins, m balls being thrown into n bins uniformly at random, and you want to look at the distribution of the balls in the various bins. And what we saw was we formally proved, we quantified it, but the gist of it was that you can, instead of thinking of it as a process where you're throwing balls into bins uniformly at random, you can assume that you're taking each bin and then choosing a number based on the Poisson distribution and putting so many balls into that bin. Right? If you think of it like that, then the distribution of balls into bins are identical in both the cases. Right? So that's what we formalized and quantified in the last lecture. And using that, we also proved that if you throw balls into bins, right, n balls into n bins, then with high probability, right, with probability at least 1 minus 1 over n, there will be a bin with omega log n over log n balls, right? So we had earlier shown that the maximum load is likely to be at most log n over log n with high probability. And the this was what we saw in the last class was that in fact there will actually exist a bin with at least so many balls, right? So that's what we did in the last class, and to prove that we use the Poisson approximation, right? So any questions related to last class? Anything to be clarified? Okay. So then today what we will do is we'll go back to a problem that we have seen before, right? This what is known as the coupon collector problem. And we'll give a tighter analysis of the problem using the Poisson approximation, right? So what is the coupon collector problem? So you have n coupons, right, uh, distributed among boxes of chocolates, say, correct? And what you want to know is so you want to collect all n coupons, and the question is how many boxes of chocolates should you buy? Right? And this is equivalent to saying the following: you have n bins, right? The bins correspond to the coupons. You have n bins, and you throw balls into bins, and you are asking the following question: how many balls should you throw so that every bin contains at least one ball? Correct? So this is the coupon collector problem as a balls and bins problem, right? We have reworded the problem, right? It's the same coupon collector problem, but we have reworded it as a balls and bins problem, right? So you're throwing balls into bins, and you want to know what is the number of balls you must throw before every bin contains at least one ball, right? And so if x is the random variable uh, corresponding to the number of balls thrown, what we have seen is that the probability that x is greater than n ln n plus cn This is at most e to the minus c. This is what we saw in the earlier lecture when we studied the coupon collector problem. We saw the geometric random variable and so on, and then we did the analysis, and this is what we saw, right? So now we will actually give a tighter analysis, right? What we will actually prove is the following. So if x is the number of coupons, right, then what you are going to show is that the limit as n tends to infinity, the probability that x is greater than n ln n plus cn is equal to 1 minus e power minus c. Okay. So it's a slightly more tighter analysis, tighter bounds that you're going to get. But the analysis, therefore, is also going to be slightly different. It's going to be a little more technical analysis. But the interesting thing is that we can do this analysis using the Poisson approximation that we have studied. So again, it's stating the same thing, right? As for large enough values of n, x, which is the number of balls that you have to throw before all the bins have at least one ball, that is going to be like n ln n plus cn. It cannot be much larger than n ln n, right? So this is what we are going to see right now. Is this clear? Any questions so far? Right? Is the goal clear? What we are trying to achieve? Okay. So before getting into the proof, let's the way we have been proving these statements is that you look at you have one algorithm that you want to analyze, which is the balls in bins problem algorithm, right? But then you say that this is a little complicated to analyze because of, say, dependent variables and so on. Let me analyze an easier algorithm, a different algorithm, right, which is easier to analyze. Let me analyze that algorithm, and then let me prove that the bounds that I get for this easier algorithm also bounds the more complicated algorithm. Right? That's what the Poisson approximation is doing. Right? The gist of that analysis is basically this: there is an algorithm to analyze, which may be complicated to analyze for now because of dependent random variables and so on. Let me analyze an easier algorithm and then prove that this analysis suffices. Right? That's what you want to do. So what is the Poisson version of balls and bins? So let's go to the Poisson case for now. So what do? You choose. So you have n bins again. Now what you do is you choose ki based on the Poisson distribution with mean mu, and then you put ki balls in bin I. Correct? You do this, and what are you interested in? What is the value that you want to compute? You want to know what is the probability that k1 is not equal to 0 and k2 is not equal to 0 and so on till kn is not equal to 0. Correct? So you want the probability that each of the ki's is not equal to 0. So this is the Poisson version of that same problem, right? In the balls and bins version, you're throwing these balls into the bins and you want to know that there is at least, what is the probability that there is at least one bin? What is the probability that every bin contains at least one ball? So here what you do, you take a bin and you choose a number based on the Poisson distribution and put so many balls into that bin. What is the probability that none of these ki's is equal to 0? Right? And in our case, what we are going to do is mu is going to be something like ln n plus c. Right? So it's not hard to see why this thing is being chosen because of what we're going to prove, right? So this is the mu that we are going to choose. So we are going to choose ki's based on Poisson distribution with mean ln n plus c. So the idea is that so if you do this, what is the expected number of balls that you will actually have thrown? So what is the expected value of summation ki? Right, that's n ln n plus cn, right? That's n ln n plus cn. Good. And what we're interested in analyzing is this probability. And we are somehow, this is the probability that we actually want to analyze when we are throwing balls into bins uniformly at random. But this probability when KIs are chosen according to the Poisson distribution is much more easy to tell, right? What is this value? What is this probability? So, what is the probability that KI is
1
equal to 0?
minus e
Yeah.
power minus mu whole power n.
Yeah. So you're talking about this whole thing, right? The and yeah, 1 minus
E power minus mu whole power n.
e power mu here is so this is n ln n plus c. This one, right? Right? Whole power n. Is that what you're saying?
Yes, sir.
Okay.
Like it should be minus ln and minus c, right?
Sorry. Yeah. So, and what is this? So this is why, because the way you will get it is that the probability that ki is equal to 0 is e power minus ln n plus c, right? Because and since it is value 0, then everything will go off. This is nothing but uh, e power minus c over n, right? And probability that ki is not equal to 0 is 1 minus e power minus c over n. And therefore, this value, yeah, what Raghu was saying, so this is, in other words, is 1 minus e power minus c over n whole power n, which is approximately equal to e power minus c. Correct. This is the sort of this is the bound that we were trying to achieve also. So if instead of throwing balls into bins, we were to do this process, then the probability that that no bin is empty is something like e power minus c. Right. So let's. So what does it say? So let E be the event that no bin is empty, right? And let X be the number of balls thrown, right? What we have just proved is that the probability of E, right, in the limit is e power minus c, right? So this quantity in the limit is e power minus in the limit it is e to the minus 1, right? 1 minus 1 over n to the n. So in the limit, this probability is what we have computed, right? So far so good. Any questions? Okay. But notice that this is not the process that we actually want to analyze, right? We want to analyze when balls are being thrown into bins, right? So if you notice, um, if you take the following quantity, right, and so you have n balls being thrown into n bins, and you want to analyze what is the number of balls you have to throw before E happens, right? E is the event that no bin is empty. You want the event E to happen, but the process is that you're throwing balls into bins. Now the Poisson approximation tells you that this probability, right, the probability that there are no empty bins, this is equal to saying is, there are no empty bins, right? Uh, okay, maybe I should revert this slightly, right? So suppose you have so the what is the equivalence that was shown, right? We said that suppose you take the Poisson process, and suppose I condition on the event that the number of balls thrown is some k, right? So suppose you have the Poisson process where in each bin you put balls according to Poisson distribution of mu, um, and now I tell you that the total number of balls that have been thrown is k. Then what you know is that the distribution of the balls is as though you have thrown k balls into the bins, right? So in other words, this probability of E says that x is equal to m, right? This is a probability that there are no empty bins, given that there are no empty bins when you do the Poisson process. Given that the total number of balls is m, this is equivalent to the probability that there are no empty bins when m balls are thrown. Uniformly at random, right? This is the equivalence that we saw last class. So to prove our statement, right, to prove our theorem, all we need to show is that limit n tends to infinity probability of E is equal to the limit as n tends to infinity of E given x is equal to m, right? So this is what we set out to analyze. This is what we want to analyze. This is the coupon collector problem. But I know how to analyze this value. Now all I need to show is this equivalence, and that will conclude. With that, I'll be able to conclude that with high probability, you only need to buy n ln n plus c coupons, right? So you want to analyze an algorithm, but you don't analyze that algorithm, but you analyze a simpler algorithm, and then you show that that analysis suffices. Okay, so this way it's slightly different. It's probably different from anything that you have seen, right? So typically when you analyze an algorithm, you take the algorithm, look at it, and then say what happens, right? You look at the various cases, loops, and everything, and then you try to prove the correctness, running time, and so on. But here we are saying that let me just throw away that algorithm for now. Let me analyze something that I can, right? I don't know how to analyze this algorithm, but I know how to analyze a simpler algorithm. Let me do that, and then let me show that analysis suffices for the actual algorithm that I set out to analyze, right? So this is what we want to prove. So now to complete the proof, all we need to show is this equivalence, correct? Any questions so far? Anything that is unclear? Okay. So then let's try to prove the statement, right? So let's try to express probability of E in terms of this E given x is equal to m, which is what we want, right? So what we do is we start out with let's say you start out this way, right? You can write probability of E this way. This is the probability of E given x is equal to m times the probability that x is equal to m plus the probability of E when x is not equal to m times the probability that x is not equal to m. Okay. This is one way to start out, right? If we are interested in this quantity, right? We need to somehow find a relation between probability of E and probability of E given x is equal to m, correct? Now, What we want to say is that, for instance, what we want to say is that this term is not going to is not going to be very large, and therefore, probability of E is somehow going to relate to only probability of E given X is equal to M. That is what we want to argue finally. But we don't. First of all, we don't know how to. It's not easy to see why these quantities must be small, right? But let's look at the variable X. What can I say about X? How is X distributed? What can I say about X? How is X distributed? The random variable X, what is its distribution?
Poisson.
Yeah, right. So X is a Poisson distribution. Why? Because X, I can write it as summation Xi, where Xi is the number of balls in bin I. And Xi I know is distributed according to the Poisson distribution with mean ln n plus C, right? So therefore, summation of Poisson variables are Poisson variables is another Poisson variable, and then the mean is just the sum of the means, right? So X is distributed as a Poisson variable with mean n ln n plus C, Cn, correct? So what we're going to use is the Chernoff type inequality that we saw for Poisson random variables. So instead of analyzing these quantities this way, let's rewrite what we want to do slightly differently. We're going to write probability of E as probability of E given that X minus M is less than 2 square root n ln m. So these are just parameters to make it make the calculations go through. Okay, so you don't need to worry about this for now. Times the probability that X minus M is less than or equal to square root 2m ln m, plus the probability of E given that X minus M is greater than square root 2m ln m, times the probability that X minus M is greater than square root 2m ln m. Okay. So it's the same thing. So this is another way in which you can write the same statement, right? And these terms, right? These two terms. Okay. So here M is so maybe I haven't maybe defined what M is, right? So M is basically ln n whatever we want to know. M balls are being thrown. So M is going to be n ln n plus C, right? So these two are basically concentration bounds, right? M is the number of balls that you want to throw. You want to say that you need to throw only so many balls. Okay. So the expected number of balls that you will throw is n ln n plus Cn, right? And you're saying that, and you know that X is a Poisson random variable. And these two probabilities are basically saying that the random variable is concentrated around its mean, correct? So for instance, so what are we going to do next? We're going to do to prove two things. So now we have the following things to prove. We're going to prove two things. The first is that the probability that X minus M is greater than square root 2m ln m. This is going to be little o of 1. Okay. So this is the concentration bound, right? M is the expected value of X. The probability that X minus M is large is very small. This is the first thing that we will show. The second thing that we will show is that, so that takes care of this part, right? For this term, that tells you that this term is very tiny term, right? It's just order little o of 1. right? Because x minus m is a very small quantity and this term is basically negligible. It's little over 1. So now what we need to do is to somehow connect this term here. So this is a large term, right? If you prove 1, it will mean that this term is something like 1 minus little over 1, right? Now somehow you need to connect this term here in this box with the probability of E given x is equal to m, which is what we want. So what you can actually show is that this probability of E given x minus m is less than or equal to square root 2m ln m minus the probability that E given x is equal to m. This is little over 1, right? What does this say? It tells you that, analyzing the event E, which is that every bin has at least one ball, right? Under the conditioning that the number of balls is close to m, is almost equivalent to analyzing it when you think that the number of balls is exactly equal to m, right? This basically means that the number of balls is close to m, which is the expectation, of x. What this is saying is that computing E with respect to this conditioning is as though you're computing E with respect to the condition that x is equal to m, which is what we want, right? This term is what we want, correct? So we'll prove these two things. And with that in hand, you can rewrite this probability as probability of E is nothing but probability of E given x is equal to m plus one small, say a little of one term, right? It's almost like this thing times a term here. This term here is another 1 minus little of one term plus this term here is a little of one term, right? So this is nothing but basically what it's telling you is that the E given x is equal to m is somehow dominating, right? It's 1 minus little of 1 plus another little of one term, right? So therefore, if you have this, then when you take the limit, right, by the definition of little of 1, right, this means that this limit is actually the limit that we want, correct? So we are using the fact that the Poisson random variables is concentrated around its mean, right? That is what this term is telling you. And this one is telling you that suppose you want to analyze the probability that all the bins are non-empty, conditioned on the fact that the number of balls is actually close to the mean, then it's sufficient to analyze the probability that all bins are non-empty, conditioned on the fact that conditioned on the fact that the number of balls is exactly equal to the mean, right? That's what the second statement is saying. And if you could prove these two things, then whatever you want just comes out of it, right? And both these statements seem believable, right? This concentration we have already seen, right? We have proved a Chernoff type bound. And this one seems okay, right? I mean, you're saying that condition on the fact that x is equal to, you're saying that what is the probability of E condition on x being close to m? And you know that x being close to m will almost always happen since m is the expectation of x. So you might as well assume that x is equal to m, right? That's what the second statement is saying. Any questions so far? Okay, so let's just briefly go over the proofs, right? The part one I'll just write down, but you can probably see it, right? So part one basically is because of the fact of the Chernoff bounds, right? Chernoff bounds for Poisson random variables. So that tells you, it gives you bounds for probability of x greater than or equal to x being upper bounded by, what was the value? Let me just see. right? So this was something like e power minus mu e mu power x divided by x power x, right? And this is also true for x less than or equal to x. Correct. And in our case, what we have is mu is m, sorry, n ln n plus cn, and x is m plus, in this case, it is m plus square root 2m ln n, right? Or, and m is equal to this value, right? M, it is m mu, which is also equal to m. Correct. So this part one basically amounts to substituting values into this equation and then checking that it is indeed little o of 1, right? So that is the part, the first part of this, right? For the second part, so what is the second part that we want to prove? Second part is the probability of, you want to say that the probability of event E, given that x is close to its expectation, is almost equivalent to the probability of the event E, given that x is actually equal to its expectation. Correct? Right. And to do this, what we do, we will start with a simple observation first, which is that look at this quantity, the probability of E given x equal to k. Okay, you can think of it as a, if you think of it as a function of k, then it is monotonically non-decreasing, right? So you can say, so given x, x is the number of balls, right? And E is the event that every bin contains at least one ball. Now, what is the probability of E given that the number of balls that you have, total number of balls in the bins is equal to k? So this, I can think of it as a function of k, right? Now, what we want to observe is that f is actually monotonically non-decreasing, right? Because the reason is that if you throw more and more balls, then the probability that every bin must be filled cannot decrease, right? If you throw one ball, then there is some probability that there is at all the bins are non-empty, which is probably 0. But now, as you throw more and more balls, the probability that every bin is non-empty cannot decrease, right? So since we are working with this balls and bins situation where you want to look at your balls are being thrown into the bins and you're looking at the number of non-empty bins, the probability that there exists non-empty bins cannot decrease as you throw more and more balls, right? So this quantity, this function, if you think of this probability as a function of the number of balls in the bins, then that is a non-decreasing function, okay? So what this means is that you can write the following inequality. What you can say is that the probability of E, given that x is equal to m minus square root 2m ln m, this is at most the probability that E is probability of E given that x minus m is less than square root 2m ln m, right? This is right. So you're given that x is equal to m minus 2m ln n. What is the probability of E happening? Then that is definitely upper bounded the fact that modulus of x minus m is less than 2m ln n, because x can be as large as m plus 2m ln n, right? So this is using the fact that this function, the probability, is a non-decreasing function. And the same thing also, let's just conclude that this is at most the probability of E given that x is equal to m plus square root 2m ln m. Right? We're just using the fact that if you're throwing more and more balls, then the probability that there must exist non-empty bins must cannot decrease, right? It can only increase, right? Is this clear? I mean, we are not we are just observing that it's only for this particular process that we are observing it. So is this clear? Any questions? Okay. So now let's just bound this quantity, right? So we just need to bound this quantity, which is minus the probability of E such that x is equal to m. Let's just bound this in this following way, right? Let's replace this by an upper bound, which is at most probability of E, given that x is equal to m plus square root 2m ln m. And this is, again, you can put a value that is lower. Again, we use the monotonicity property of this probability to say that I can replace this by the probability that E given x is equal to m minus square root 2m ln m. Right? I can give an upper bound this way. And how do you compute this difference? Right? So what is this probability? Right? This difference of these probabilities. Right? It's saying the following thing, right? So if you notice, so let's let's look at it this way, right? So you are looking at the probability of event E, which is that every bin is non-empty, given that you have thrown m plus square root 2m ln m balls, right? And here what you have is the probability that there are no non-empty bins when you have thrown m minus square root 2m ln n balls, right? So this is nothing. So if you look at it, this quantity, right, what does it say? This is saying that what is the probability that when m minus square root 2m ln m balls when so many balls are thrown, then there is an empty bin, but after m plus square root 2m ln m balls are thrown, all bins are non-empty. Right? For that, you can think of it this way, right? You're interested. So let's say you look at this probability of E given x is equal to m plus square root 2m ln m, right? How can this happen? This can happen in two ways. One is that, so let me call this event by a new name. Okay, let me call this event by the name A. Okay. So when can A happen? It's the probability of A happening given that uh, so let me just so let's define these two events. Okay, let me just define two events. This is the event A that is of interest. So A is the event that there are no empty bins when m plus square root 2m ln n balls are thrown, which is what we are interested in. And B is the event that there are no empty bins when m minus square root 2m ln m balls are thrown. Right? So can you write this way? So you can write probability of A is the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B, right? B complement. What is the probability of A given B? What is the probability of A given B? Yeah, that's 1, right? Because if there are no empty bins when you have m minus square root 2m ln m, then surely there are no bins when you throw more balls, right? So this is the case. And what is probability of B? B is actually what we want, right? So this is the probability of E given x is equal to m minus square root 2m ln n. And this is the probability of E given x is equal to m plus m minus square root 2m ln n. Right? So what we are interested in is this event. Right? So the probability of A given B complement into the probability of B complement. Correct? How do you upper bound this? So notice what do you want here, right? So this is one place, right? If once you do this at this step, you don't really want to go ahead and try to compute this probability, exactly. That might be too tiresome, too difficult. Recall what we want. We just need to show that this is equal to little o of 1, right? That is all that we need to show. We don't need to do anything more. We don't really care what these numbers are actually. All we want to show is the asymptotic behavior of these things. Right? So how does it follow? Why is it little o of 1? Can you think? So what does this mean? You have thrown m minus square root 2m ln m balls, and after that there are empty bins. But now you throw an additional 2 times square root 2m ln m balls, and then every bin is empty. Every bin is filled. Right? What is this probability? How do you say that this is little o of 1? Right? You don't need to go into direct calculations, right? So whenever you can approximate, whenever you do these analysis, whenever you can approximate, then you try to approximate, right? Typically you don't actually want exact values, right? So when you study probability in combinatorics and so on, you typically want to try find out the exact values of these probability, these numbers, right? What is the exact probability? Here we don't really care about the numbers. We are more interested in the asymptotic behavior of these probabilities. Right? So you just need to approximate it. So why is it little of 1? So maybe I'll just leave it. It's there in the book anyway, but you can think about it and see how you can show that it is little of 1. Okay. So this, so what does this show? It tells you that this quantity here, which is what we wanted to bound, this is bounded by this inequality, which is the probability that in the first m minus square root 2m ln m balls, there is at least one empty bin which gets filled in the remaining 2 times square root 2m ln m balls, right? And that these are the two statements that we needed to prove, and that basically tells you that that concludes the proof, right? Because that's all we wanted to show, right? As it's written here, once we show that we take the concentration inequality for Poisson random variables, and then the fact that the probability that there are empty bins, right? There is no empty bin, assuming that the random variable, the number of balls, is close to the mean, and the same probability when you assume that the number of balls is exactly equal to the mean, then they are almost similar. They are equivalent. Their difference is little over 1. And that concludes this proof, right? So that also concludes. So that basically tells you that this approximation that we are doing is fine, right? So it implies this statement here, right? And by the Poisson approximation, this is the number of this tells you the probability that when you throw m balls, right, what is the probability that there is at least one, there are no empty bins, which is what we wanted to analyze in the case of coupon collector. Any questions regarding this analysis? Anything that you want me to go over again? Okay. So then, so this is regarding the balls and bins. So we have analyzed various scenarios for balls and bins. So remember that the reason we started out with this balls and bins is that it is a paradigm which captures a lot of different real life problems, right? So one such problem is hashing, right? So which is what we are going to do in detail next, right? So one such problem is hashing. And we said that, so in the analysis, all the analysis that we have done regarding the size of the bin, what we've actually shown is that if you use chain hashing, right, which is that, so there are a couple of assumptions that we make. So you're doing hashing where the hash function is a truly random function. We have assumed that, right? That is what the balls and bins is assuming, right? You have a truly random function, right? And say you use chain hashing, which is basically that if two elements hash to the same location in the hash table, then you store them as a linked list, right? So what can you say about the expected running time of chain hashing, right? What is the expected running time of chain hashing? Say you are storing n elements in an n element array, right? You have n elements to store, right, that you want to store, and you have a hash table of size n. What is the expected running time of chain hashing? So so let me just rephrase it. Expected running time for searching an element. So searching one element, right? So when you want to analyze the running time, you want to look at the search procedure. So given an element X, how long does it take to search that element, to check whether that element is there? So the expected running time is actually order 1, isn't it? Because the expected size for any expected load, right, in any position, if you take any position, the number of elements that get mapped to that position is just order 1, right? For every element, the probability that that element gets mapped to that location in the hash table is 1 over n. There are n elements, so the expected number of elements that are mapped into that particular location is order 1, right? So if you take a truly random hash function and then you use chain hashing, then the expected running time is order 1. And as Sarthak is saying, the worst case running time is order ln n by ln n, right? This is the max load, right? The max load we said is going to be likely to be ln n over ln n. So in the worst case, this is our running time, right? The expected running time is order 1, but the worst case running time is ln n over ln n. Right? This is the case for chain hashing. Now, we can ask a different question for hashing, which is that suppose I want to store these elements. So how does the hashing work? So you take the element, and in the table you store the entire element, right? And then you basically go, and when you want to search, you look at the location, and then you check whether the number of whether the bits match corresponding to the element and the element that you have in hand, whether they are equal or not. Okay. So if you want to store n elements in a hash table, how many bits per element do you need? What is the number of bits per element that you need to store in the hash table to do this searching? You have n elements you want to store into the hash table of size n. How many bits will you need to store per element if you want to do the searching? It's a slightly different question, right? So it's not exactly talking about searching and so on, but you're looking at the space required to store these elements. Yeah. So as Indranil said, it's log n, right? You need log n because you need to know which is the element, right? You need log n, and you can't avoid log n, right? Because otherwise you won't know which element is there. There are n elements. The only way you can information theoretically, you need log n bits to identify an element in that set. So therefore you need log n space. But now, is it possible that you can store elements in a table, hash table, where each element requires less than log n bits, right? So you can't do this if you want to get the correct answer always, right? So is it possible to trade off the space required in the hash table if you are willing to have some amount of error in the find and search operations? Okay, so it's a different question, right? It's a slightly different question related to hashing, and this is what we will see next, right? So there is a data structure that can do this. It's practically used, and it's used in a lot of different scenarios, right? But we will not be looking at the practical implementation of this data structure, but rather its theoretical analysis. And this is what is known as the Bloom filter. Okay, so it's used a lot in many scenarios, but we want to look at the theoretical analysis of this data structure. So you're going to store n elements, but you're going to use less than log n bits per element, but you're willing to have some amount of error in your find and search operations. And how do you do that? Okay, so that's what we will do in the next lecture. Okay, so we'll stop for now. Any questions? Any clarifications?